Okay, this is 7.3. We have another method for determining volume of these regions being uh, generated by revolving regions about the x or y axes or axes parallel to those axes. Um, it's called the shell method. Okay. Okay, so we'll start with the x-axis rotation. So here's shell working with horizontal axis of rotation. And let's take a look. Okay. So let's maybe take a region like this. And we want to rotate it about the x-axis. And for this kind of rotation, the rectangle is going to be parallel sort of to the axis of rotation. Okay, so it's this thing that's being rotated about. So in particular, it'll be located at some position y sub I. The width of the rectangle will be change in y. And then you'll have some sort of function g of y to tell you the length of the rectangle. Okay, okay. And then we're spinning it around this x-axis. So the end result of this red rectangle being spun would be this kind of object. Something like that. So we need to figure out the volume of this thing, and then our running man, you know, the Riemann sum basically is trying to draw this guy. Oops, butchered his leg there. He's running in this direction, and then he's collecting this bag of volumes basically. So it's a sum of volumes that he's collecting this time. Okay, so we need to know the volume for these objects that we're collecting, and then if we get the volume of these things, it'll give us an approximation for the volume of the object that's being traced out by revolving this, I guess, this rectangular region about the x-axis. Okay. Okay, so what I'm going to do is take this thing, right, and you know, here's where the old rectangle was from this picture. I'm going to take this thing and I'm going to cut it. All right, I'm going to take some scissors out and cut the thing right along there. And then I'm going to unfold it and take a look at it. And so there's that. I need to figure out some dimensions on this thing. So I could figure out the volume. I mean, not as it says, it's a rectangular solid, so I need length, width, base. So you know, taking into consideration where it came from, I know one dimension. This dimension right here is a change in y. Okay. The length of the rectangle, which is now the height of this thing, is g of y. And then I have to figure out this length here. And I claim I kind of know this length via my knowledge of circumference of circles. Okay? Because this length here is just the circumference of this circle. So the formula for the circumference of circle is 2 pi r. So it's like some 2 pi times the radius of the circle. So the radius of the circle is just the length from here to here. That's the length from here to here, right? So the length from there to there, in this case, is this y sub I thing. Okay? In general, though, it could be different if you're oriented in weird ways. So instead of writing y sub I, we'll write some function of y, p of y sub I. Okay? But in this particular case, it does turn out that p of y sub I is just y sub I. Okay, so these volumes, the running man is picking up and putting into his bag on his shoulder here. These volumes will just be this times this times this, which is 2 pi p of y sub I, g of y sub I, times change in y. Okay, for our sort of these shell objects that we're worried about. Okay. So at the end of the day, the actual region, you know, what does this thing look like? It's kind of like, it's going to look like a, I don't know, a bunch of maybe like a birthday cake, I guess, you know. And it'll be nested. So this would be this lowest rectangle, and then there would be other rectangles kind of covering up. I don't know, it looks something like this thing here would be the approximation that you're working with. At the end of the day, there's a hole in it, obviously. So this would approximate the volume of this, I guess it's kind of like a bagel type object that's been spun out. Then when you, so this would be the sum of these v sub i's that the running man is picking up in his bag. And then you take the limit of that as the number of little rectangles goes to infinity, or the number of little shells goes to infinity. It's going to be the sum from I equals 1 to n v sub I. And then we would get our integral for this scenario, which would be 2 pi integral p of y. They're going to call it g of y, h of y, because it's kind of like a height of the rectangles. It's you know, literally it is the height of these things here, these shells, and then dy, and we're going from something like c to d. Okay. But at the end of the day, this is our new sort of integral that we want to work with. And you know, thus far we have the integral for finding area between curves. It's just difference. Then we have the disk integrals, which is a pi r squared scenario. Then we have the washer integrals, which is pi integral big radius minus little radius square, and they're both squared. And now we have this this character here, which is our shell integral. And you'll find that the shell integral is good for objects that have holes in them. Okay, so anyways, let's get in there and start worrying about actually doing these things. This is problem 29 here. And we have y equals x cubed, y equals 0, and x equals 2. And we want to rotate this region about the x-axis. Okay. Okay, so in general, when you're doing these, you want to identify the radius function and then that height function, the p of y and then the h of y, in order to get this thing to pan out, so to speak. Anyways, let's go ahead and graph the region. So a cubic in our region is going to look like that. We're going from y equals 0, which is the, sorry, y equals 0 is the x-axis, to x equals 2. Then at 2, y is 8, so it's intersecting up there somewhere. Sorry, my graph isn't perfect. But this is the region we're rotating, and it's about the x-axis. Okay. So you want to identify your rectangles. These times and the shell is parallel, right? So the rectangle for the shell is parallel to the axis of rotation. There's my little shell. So I need to identify then my p of y and also my h of y for this particular rectangle at location y sub I, right? So the p of y is the radius of this thing that's being rotated out. So this particular shell maybe looks like this. Okay. Sorry, this particular shell probably looks like this after it's rotated. I need to know this dimension here, which is the radius dimension, the p of y. And I also need to know the h of y, which is this dimension here. Okay. So the p of y is usually just going to be your y position. Okay, so the distance from here to here is p of y. It's the radius, and it's usually just y sub I, unless you're rotating about a non-axis. H of y, then I need to know this dimension from here to here, and I'm going to have to work with this function in order to pull this off. First thing you know, this is not a function of x as it sits. We need x equals something, so you just take this character and take the cube root of both sides. In other words, raise both sides to the 1/3 power. And then you end up with x equaling y to the 1/3. So that will be our formula to give us the distance from here to here. But we need to know this smaller distance, right? So the smaller distance we think of as a difference of distances. It's really the difference between this distance and this distance. Okay, it's that difference which gives you this distance here. Okay, so the longer distance from here to here, or if you'd rather from here to here, is just going to be 2. And then we need to subtract this distance, so the distance from here to where the rectangle begins, this hole, and that would be given by this formula here. Okay, so it would be 2 minus y to the 1/3. And then, and we're going to leave it in terms of y, not y sub I at this point. So we're not working with the Riemann sum anymore. So you take all this information and plop it into your integral. So 2 pi integral, and we're going from the running man. So if I were to go ahead and draw my running guy, and let's go ahead and put his bag on as well. So he's accumulating all these rectangles, or all these shell volumes. The sum of these v sub i's. Okay. he's going from here to here, right? So he's going from 0 to the intersection of this curve and this curve. And what is that? Well, at the point 2, if you plug 2 into this formula, the y value is 8. So 2 cubed is 8. So I'm going from 0 to 8 on my integral. And then it's just p of y times h of y dy. And that's your integral, and you would, evaluate, and you'd be happy. Right? So yay. I'm going to leave the integral to you and just move on to the next problem. Okay, let's take a look at number 17. So we have y is 1 over x. Just in case we need it, let's go ahead and rewrite it as x is 1 over y. I believe the book is kind of showing you the region they want traced out. They want this function from y, or rather x equals 1 to x equals 2, right? So you would draw that out by indicating these two vertical lines and then this horizontal line, y equals 0. Okay, so x equals 1 to x equals 2 is this region here. Y equals 0 is, of course, the x-axis. And then this function from here to here, you can kind of just get the endpoints, and that'll tell you a lot about what you're dealing with. But at 1, this thing is at 1, so it's right here. And then at 2, this thing is at 1/2, right? So it's about right here. And then, it's concave up. If you took the second derivative, it would be positive. So it looked like that. We're spinning around the, what are we spinning around? I think it's the x-axis. My notes don't really say, but we'll presume it's the x-axis, okay? Okay. This guy's kind of a troublemaker, and it sort of is pointing towards the issue, when do we use shell, when do we use disk? Okay. So if you use shell here, you're going to kind of be in a world of hurt. Not really, but as close as you can get in mathematics to being in a world of hurt. The problem is you have two different regions, basically. Okay, so you have basically this region 1, and then this region over here, we'll call it region 2. And the issue is they require different height functions for your rectangles in those regions. So the rectangles in this first region have a constant area. Okay. So maybe we should say, all right, this is region 1, and then region 2 over here. I don't know why I use Roman numerals, but there it is. So in region 1, as usual, our radius function, p of y, is just going to be y, but the height function, like I said, is constant. It's just, it's always going to be 1, right? The length of this thing from here to here is always 1, so h of y is 1. On the other hand, in region 2, it's a variable height. So the rectangles look like this. The radius function still is just y, but the height function now will be a little bit different, right? It's this distance to the curve minus this distance here to the bottom of the rectangle. So the distance to the curve is just 1 over y. For this particular y, if you plug into this equation, it'll tell you the distance from this point here to the top here. Okay, so it'll be 1 over y, but then you have to subtract away this big whole business here. So then you're subtracting away 1. So it's, again, you think of it in terms of distances. It's this distance here. Okay. And then you're subtracting away kind of the donut hole, this distance to here. So this distance minus this distance gives you this red distance here. Okay. And then that's this formula that you're worried about. And then the running man is accumulating his volumes in this direction, right? So let's put his bag on him. He's doing a sum of these v sub i's. So our integral then, 2 pi, there's two integrals, right? One for this first region, one for the second region. So the first integral from 0 to whatever this point, so it's 1/2 on the y-axis of y times 1 dy, and then plus 2 pi times the integral from 1/2 to 1 of y times 1 over y minus 1 dy. Right? So like I said, this is probably not the direction you want to go in when you're dealing with these kind of regions, because at the end of the day, it's much quicker to just do a disk method and let your running man go in this direction for the disk. Right. So in that case, for a disk, you have the integral pi r squared h, right? So pi, our radius function is just 1 over x squared, and then dx, and we're going from 1 to 2. Okay, you'll get the same answer as this, it's just this one heck of a lot quicker. Right. Okay, anyways, let's take a look at shells now with the other rotation. So section 2 now, shells, vertical rotation. And for the vertical, all your formulas will be in terms of x. So it's basically whatever axis the base of the rectangle is kind of attached, or whichever axis the rectangle is perpendicular to is kind of going to give you your variable. So this is in terms of y, because the base of the rectangle would be on the y-axis if I projected this thing onto here. So in this case, when you're doing rotations about the y-axis, the rectangle will be something like this, and we're rotating this rectangle around. Its base would be projected onto the x-axis, so our formulas are going to be in terms of x, is what I'm getting after. Okay, so in particular, if we had some sort of region that we cared about, right, being rotated about the y-axis, okay, the shell rectangles are parallel to the axis of rotation. So I'm rotating this region, and the end result would be this kind of figure. Sort of. Right, I need the volume of that figure, so I come over here and get the formula for this guy. I need this dimension, I need this dimension, right? So this dimension right here is just the height of this rectangle. So if this is some function, we'll say f of x sub I, and this thing is located at x sub I, its width is change in x, then this dimension right here would be f of x sub I. And of course we want 2 pi f of x sub I. And then we need this dimension here, which we'll call some sort of radius function. But in this case, it's just plain old x sub I, right? But in general, we'll want sort of a radius function like last time. And then, of course, change in x for the width. Okay. Alrighty then. So our running man this time is going in this direction. He's going through and stealing. Let's turn him into a criminal, right? Let's put a little mask on him. He's going through and stealing all of these volumes and throwing them into his bag. So here's our sort of Riemann sum. And then as you take the limit of that thing going to infinity, again, as the number of rectangles goes to infinity, there's of course other ways of defining that thing. In more general terms, it's the width of the rectangles goes to 0 or something. We're not going to get too carried away with that. Let's just take this guy and plop him in here. So get b sub I, and then we have the integral from, if this is a and b, integral, whoops, lost my 2 pi, integral from a to b of these guys here. So in general, we'll say f of x sub I is some sort of height function, and then the radius function we want as well. I think the book usually puts the radius function first. Okay, so it's just the same formula as before, but now in terms of x. Okay, long story short. 90% of this was just so I can draw my my little criminal dude. I just love that. He looks sweet. All right. So, anyways, let's get to business here. This is problem 11 from the book, as usual. Let's take a look at this region. Y equals square root x minus 2. Y equals 0, x equals 4. I want to do a y-axis rotation. Okay. So there we go. The square root of x minus 2, where is that located? So you just take the square root function and shift it over 2 units. Y equals 0 is the x-axis, x equals 4 then. That'll be right there. And this is our region. We're rotating about the y-axis. And let's identify our rectangles for shell. They're always parallel. Okay, so there's my rectangle. I need to identify my radius function, p of x, and then my height function, h of x. This time will be pretty easy, right? So this, location for a general x sub I, the distance from here to here is just the x value. Okay, so it's just going to be x, and that happens all the time unless your axis of rotation has been shifted over. Okay, it's always p of x is x or p of y is y for x or y axis revolutions. Okay, then h of x is just the distance, or sorry, just the length of this, height of this rectangle. So it's the distance from here to here, which is just given by this formula. To know this distance from here to here, just plug x into this and you get it. So this is square root of x minus 2. And so our integral will be 2 pi integral from 2 to the 4 of x times square root of x minus 2 dx. Okay. And of course our running man, our little criminal guy, is stealing our our volumes in this direction. Okay. Okay. Let's see what else we got. Oh, of course, shifted axis revolutions, and then we'll do like a compare and contrast, where we'll do disk versus shell. Okay. All right, so shifted axis rotation, section 3. The main difference now is that radius function. If you remember before, what I was saying is usually the radius function is always just either x or y. Now it won't be, right? So p of x is not x, and likewise p of y is not just going to be y. Here's 25. Problem 25. We have the region y equals x squared, y equals 4x minus x squared, about the line x equals 4. So I'm rotating about this thing. Okay, I want to get a picture of this guy, so I kind of know what this guy looks like. This guy, maybe get a vertex and all that jazz. To get a vertex of a parabola, you just take its derivative, y prime, and set it equal to 0. This is 4 minus 2x. So 2x is 4 and x is 2. Right? Plug that back in for the other coordinate of the vertex. So it's 8 minus 4 is 4. So our vertex is 2, 4. Okay. And the intersection point between these two characters, what is that? Well, 4x minus x squared is x squared. You set the two equations equal to each other, right? So you get, moving this junk to the other side, we're going to have 2x squares minus 4x is 0. And then factor out 2x, so you get 2x times x minus 2 is 0. So 2x is 0. X minus 2 is 0, so x is 0, and x is 2. So apparently 0, 0 is one intersection point, and then 2, 4 must be the other one. So let's get a picture. Picture one here. 1, 2, 3, 4. There's the axis we want to rotate about. Okay. The picture then, 2, 3, 4. This guy is a downward facing parabola like this. So it'd be something like this, from here to here. And then it's going to go do something else, but we don't need that whole thing. We just need the region where they intersect. And the intersection points are found 0, 0, and then 2, 4, so it's going like that. Anyways, this is the region at the end of the day. There it is. I want to rotate it about this axis for shell. The rectangle is always parallel. So our little rectangle is going to be sitting here. Okay, I need a formula for that character. What is my formula then? So I'm in terms of x. Okay, so let's say this is x sub I right here. The radius function will be a little different this time. The height function I think we can kind of get though. So this length here is just the difference between the length from here to here and the length from here to here. So that's just going to be the difference of the functions, right? So it's this length from here to here, which is given by this formula. So this is 4x minus x squared, and then you subtract away this distance, which is given by this formula, so minus x squared. On the other hand, then, I need to know the distance from here to here. right? So let me do that in green or something. I need to know this distance. Let me translate that distance to right here. It's this distance I'm after. Right? That's going to give me the radius of this shell. So, again, let me just remind you kind of what the shell would look like in this case. If I took this and rotated about this line, it's going to look like this at the end of the day. So what do we got? What are we dealing with here? I need two things. I needed this distance, and I already got that distance. That was just the height of this little red rectangle. So the rectangle right now is sitting here, right? But I also need then this green distance, which is the radius of this particular shell. And it's easy, it's just a matter of subtracting again. So the green distance is just the distance from here to here minus the distance from here to here. Okay? So it's this distance minus this distance. This distance is a constant, it's fixed at 4, right? And then this distance from here to this particular rectangle located at x sub I is just x sub I. So it's just going to be this distance, which is 4, minus this distance, which is x. So it'd be 4 minus x at the end of the day. It's not so bad. All right, so I need to now dump everything into my, let me draw my running man. Or I like to think of him as a criminal now. And he's stealing all of these volumes and putting them into his bag. Okay, so my integral then for this scenario will be pi times, 2 pi times p of x, 4 minus x, times h of x. I'm going to clean that up a little bit. 4x minus x squared minus x squared is minus 2x squared dx. And I'm going from 0 to 2. The running man is collecting shell volumes from 0 to 2. And then you would, do your integral. I'm done on my integrals. Okay, so the last but not least, I'm going to take a look at a question from a test from, wow, this is 7 years ago now. Time flies. So here's problem 8, test 2. It's from summer 2013. Okay. And they want you to rotate the region y equals 1 all over square root of x plus 1, y equals 0, x equals 0, x equals 4, about the axis, about the x-axis. Okay. So on a test, I won't really tell you to do shell or to do disk or washer. You just have to figure it out yourself. Okay. So in this problem, let's look at shell versus disk and see which one's easier. So first, we'll do the shell. Okay. So drawing out my region here. Y equals 0, x equals 0, and then x equals 1, 2, 3, 4. And then this guy, so at 0, it's at 1. So I'll just put 1 right here. My axes are not. So this is 1 here, 2, 3. This isn't 1, so maybe I should mark that. 3, 4. And then at 4, it'll be 1 all over the square root of 4 plus 1, which is square root 1 over square root 5. Okay, so that would be down here more. And so my region is this. I'm rotating about the x-axis. Okay. So shells are always parallel, and already there's an issue, right? So when you do the shell method, there's going to be 2 different regions, region 1 and region 2. Okay, so already it's kind of annoying. So for region 1, I'll need some formulas. H of, and the rectangle has its base on the y-axis, so everything's in terms of y. So I'll need P of y and H of y for this particular rectangle. I'm looking at position y sub I. So P of y and then H of y. P of y, because we're rotating about this axis, is just going to be y. It's the distance from here to here. In other words, location y sub I for this particular rectangle tells you the radius. And then I need a function for the height. In this case, it's constant. It's always going to be a height 4. This distance from here to here is always 4 in that first region. So I'll write 4. And then my integral in that case, and my running man is, and I'll not do all the details of the criminal, little bandana, well, no. Okay, so there he is, just put a hat on him. He's going in this direction anyways, right? And first he'll go from 0 to this intersection point. I think it was 1 over root 5. So my integral will be 2 pi integral from 1 to 1 over root 5. So that's even more annoying. And then it's 4 times y dy. Okay, so that's my region 1. And then region 2, I'll need another set of formulas. So I need a P of y again, and then an H of y. P of y again will just be y. But my H of y is variable this time. The height of this little rectangle that I just drew is variable throughout this region. And its height for a given particular y sub I will be given by this formula here, but it's not in terms of y, right? So I'm going to have to change that. So square both sides, and I get y squared is 1 all over x plus 1. I need to solve for x. So I guess cross multiply or something. You get x plus 1 is y squared. And so x is equal to y squared minus 1. Okay, so that'll be my height function, y squared minus 1. And now I can go ahead and write my other integral, so plus 2 pi times the integral of 1 all over root 5 to 1. And then I have y times y squared minus 1 dy. Okay, so you have 2 integrals if you are unlucky enough to attempt it in that. And I think I screwed up my formula there, back up here. Yeah, I did, sorry. So when I cross multiply, I should have 1 over y squared. Sorry. So that would be 1 over y squared there minus 1. 1 over y squared minus 1. And inside here, 1 over y squared minus 1. Sorry. So more like that. Let me rewrite that. So it's going to be plus 2 pi integral from 1 over root 5 to 1 of y times 1 over y squared minus 1 dy. Alrighty then. So that was a nuisance. Let's look at the disk method. And you'll see this disk method is the way you want to go. So again, let's set up our region. Same region. Right. So something like this. But if you use disks, there's none of this region 1, region 2 business going on. Okay? So remember, for disks, you need a radius function, r of x. The region that this thing is worrying about looks like a disk this time. So it'll be this kind of object where the little rectangle is right here. Okay. And then to get the volume of this guy, you need this radius function, this r of x formula. And that's pretty much it. You know, this is change in x right here. Okay, and then it's just pi r squared h. The height is this, and then we just need the square of this in our integral. You know, compare and contrast that thing to over here, where your little, you know, volume regions are shells in this case. I guess it'd be kind of hard to draw it where it's sitting, but its region in this case would be kind of like this. So the region that's being generated by rotating that about the x-axis is this. So this is the shell, and then versus over here is the disk. Okay. And the running man for the disk is opposite to what it would be for the shell. So this guy's going in this direction and stealing up his volumes. Okay, so anyways, the formula for the radius here is a lot easier, right? It's just this dimension that I'm after, which is given by our original formula. So r of x is 1 all over the square root of x plus 1. And then dump everything into our integral. So it'd be pi from 0 to 4 of r of x, 1 all over square root of x plus 1 squared dx. And that's it. So a lot easier. So you want to be wise in your decisions between shell and disk. Okay, this time you want to do a disk. Okay, that's good enough. We'll see you next time.